Good morning, everyone. Welcome to our lecture session. Before we get started, please make sure you visit the SI Canvas page and take a short survey on your availability. We want to help you in some of the problems you may have so far. If you haven't take a short survey on SI Canvas page, please do so as soon as you get a chance. I did announce this past Tuesday regarding that short survey. Please take advantage of the resources so that you are well prepared for the quizzes as well as the exams. If you missed the last session, we started. Yeah, somebody said they cannot hear me. Can you hear me? Oh, yeah, thank you. Yeah, I'll get back with you, Jenna. I'll get back with you about the GRE. If you want one-on-one help on that, please let me know as well regarding that. Maybe it went to my junk mail. So the remainder of chapter 7, we went as far as section 7.7, which I believe, all right, you're already familiar with the groups on the periodic table. Element are arranged according to, the vertical columns. There are 18 vertical columns, and they are 7 horizontal rows we call periods or series. All right, what we will see in chapter 8 will be basic chemical bonding, which is tied to how the groups behave or the properties of the group. Let me just share the periodic table here, which I know you are familiar. When you look at the periodic table, this is just, sample periodic table. Some periodic table, they may have different colors, but nevertheless, all the elements are arranged according to increase in atomic number. And group 1, they have special name we call alkali metals. These are group 1A, group 2A, group 3A, group 4A, the nitrogen group of nitrogen, 5A, 6A, the oxygen group or the halogen. Sometimes we call these halogens. We have halogens, group 7A and group 8A. These are the representative or main group elements. So when you look at the PowerPoint slide here, as far as the groups 2A, 1A, 6A, or oxygen group, 7A, halogens group, meaning salt forming unnoble gases, those are the groups we will be using. Yes, Jason, I'll post that. I do have the lecture recording for that. It will be available today. So group 1A, we call those halogens. Alkali metals, even though there is hydrogen in there. It's got a special property. We will look at that. Alkaline earth metals, group 2A, oxygen. These are the groups we will look at in section 7.7. Other than that, we look at the other periodic trends, the electron, the effective nuclear charge, the trend on the periodic table, how to calculate the effective nuclear charge, trend on the metallic character. You should know that. Trend on atomic sizes of both neutral atoms and the ions. So that's what I want you to remember as far as the periodic trends are concerned, all right? I want you to remember the trends we have looked at so far in or on the periodic table. So I want you to uh, read, make your own notes so that at least, all right, at least you will be in a position to answer question regarding those trends, all right? Regarding those trends, which we will look at it in terms of the periodic trends on how those atoms react, all right? So now let's see what I want to see is the group one. How does group one metals react? How does group one metal react? We know that group one metals, they have what? They have group one metals, they have one valence electron, and the group 1A, all of them, they have one valence electrons, and you know where they are. They are on the first column on the periodic table. Typically, they are shiny. That means what is meant by last year. They are good conductors of electricity. They are soft metals. I recall in graduate school, I was working with sodium and it is stored in mineral oil. And every time I was picking up the sample of sodium, I used to cut with a knife. They are soft metals. They are soft metals. So that is what group one basically are, except for the lower ones, which are radioactive. Table 7.4, if you look at table 7.4, there is a pattern here in terms of physical properties. Look at the atomic radius. What happened is you go down a group. Just like the trend on the radius we looked last time, all right? This is what you see that every time you go down a row, the number of shells keeps on increasing, and it explains why you see this radius increasing in angstrom, all right? Increasing in angstrom. And the one I here, this means what? This means fast ionization energy, fast ionization, and we defined this term last time, fast ionization what? Energy. Because, all right, because lithium or going down the group, the closer the electron, the closer the S1 electron to the nucleus, the harder it is to remove. Remember, ionization energy is defined as the amount of energy required to remove an electron from a neutral atom in its gaseous state. And the reason why you see this is decreasing down the periodic table is because cesium, the outermost electron, is far away from what? From the nucleus, and because of the shielding, it is easier to remove. There is also the density which is increasing. They have low densities, low ionization energy, as compared to what we look at earlier on, group 8. You need to know their trend for alkali metals, their properties, how ionization energy changes as you go down the group, the atomic radius as you go down the group, and you should understand that melting point also decrease as you go down the group. This is just an illustration that alkali metals readily react with water. The reactions are highly exothermic. That means it keeps away heat. It keeps away heat. I don't think you'll ever, unless at a higher advanced chemistry lab that you will get a chance to work with metallic sodium, for example, because of the danger of igniting the when exposed to H2O. Even water in the atmosphere uh, is enough to cause an explosion. Explosion because when it react with H2O, hydrogen is given off, and it's just gonna be like the hydrogen bomb, which is something different. Well, for metallic oxide for group 1, I don't want us to just forget about the metal oxide. I want us only to know the trend on their reactivity as far as the group 1 metals are concerned. Will you expect rubidium metal to be more or less reactive? If you look at this, if you look at the trend on the picture on this side, it's going down the group. This means you need to circle, assuming that this is an exam, you need to circle the rubidium. You are expected to know that what is the chemical symbol for rubidium? From the periodic table, all right, rubidium is just below potassium, okay? And that means we expect that to be more reactive. This indicates that as you go down the group 1 metals, the reactivity increases because of low ionization energy, which explain, all right, low ionization energy, which explain the highly reactiveness of what? Of group 1, of group 1. Now, certainly I know you will take the, or you do the, an experiment on flame test. You know, there is an experiment for this course which will call for using the flame wire to characterize or to qualify if there is qualitative analysis, if there is either of group 1 metals, even group 2, they have characteristic flame for lithium, for sodium, for potassium. They have characteristic wavelength, and this is explained. The colors you see emitted by the flames has to do with the excited electron jumping from higher energy level. Remember what we talked about earlier on in porous hydrogen atom. Assuming that this is an electron in its ground state, negatively charged, and there is a photon of light, this will excite this electron to a higher energy level. We call this excited state. And it will drop down to where it was originally, and a photon of characteristic wavelength is given off based on the wavelength. You will see this. So excitation and then relaxation coming down to ground state. And all these explain why you see that. Even, all right, in, okay, in fireworks, it's just 4th of July was just the other day. We always enjoy the fireworks. You see different colors. It has to do with the different metals in those fireworks that electrons are excited to higher energy level. When they drop, they emit light of characteristic wavelength. No one will expect you to, memorize the colors here, but if need be, you'll be given. You need to know which corresponds to what. Your friends, all right, at home, they just enjoy the fireworks, but at least you can look at it with a different perspective, with a different understanding, explaining electrons coming down to ground state and emitting photon of characteristic wavelength. As compared to group 2, these are group 2 metals. We're also looking at the physical properties. These are just some of them. There are group 2. If you look at the electron configuration, and by the way, this is the shorthand using group 8 elements, all right, to represent the core electron in parentheses. The 2, 2, 2, 2, S2, S2 means group 2, and compared to group 1, all right, if you look at the fast ionization energy 899, if we go back to group 1, let's see ionization of 521. Because we are increasing the nuclear charge, which means the force of attraction keeps on increasing, which leads to higher ionization energy compared to group 1. Remember, the ionization energy increase going to periodic table because of increase in the C effective or the nuclear charge. Turns out that the density increases down the periodic table. Melting point keeps on increasing, decreasing down the periodic table as well. They have high densities and melting point compared to group 1. Their ionization energies are low, but not as low as those of group 1. So compared to group 8, we'll see later on that ionization energies for group 8 is way higher because it's hard to remove that valence or those two valence electrons for group 2. They readily form positive 2 cations. By losing their valence electrons, they form positive 2. Except for beryllium, you always see this cation, Mg2 positive 2, calcium, of course, positive 2, strontium positive 2, because of what? Loss of 2 electrons, valence electron, the electron in the outermost shell, electron in the outermost shell. Group 1, they form positive 1. Group 2, metals form positive 2. Beryllium, in group 2, beryllium does not react with readily with H2O, but magnesium react with zinc. Group 1, they react with H2O. Group 1 and 2, you'll see sometimes being referred to as active metals because of their reactivity. They readily react with H2O. The reactivity keeps on increasing as you go down the group, so that the top is beryllium. It does not, but as you go down, magnesium, calcium, strontium, barium, they do react with H2O. Yes, I'll get back with you, remain after the class, Large, and I'll get back with you. I got your question, so that we look at it. Now, group 6A, remember we jump now from 1A to A, we are going to 6A, 7A, and 8A. In a similar fashion, from electron configuration, group number corresponds to the valence electron. Electron in the S and P sub-level, 2 plus 4 is 6. All of them, they have 6 electron in the outermost shell or the highest N value, which means the greater the ionization energy here for group 6A compared to group, all right, compared to group 2A and 1A, because of the increase in the nuclear charge, it keeps on increasing as well. Melting point increase down the periodic table because of the same reason that the nuclear charge keeps on increasing. Therefore, it's hard to melt that because of the number of electrons. There is a mixture of metals and non-metals going down the group, all right? Tellurium is a metalloid. You know where metalloids are on the periodic table. These are metalloids or semi-metal. And group 6A is right here. Selenium, tellurium is right here, which is metalloid. Even polonium, this is a metalloid as well. Some others mention this as a metalloid as well, or semi at some time. And livermorium is some metal. You'll never see some of these because they are radioactive. They just make it and they disappear. So tellurium is semi-metal. Polonium is a radioactive. It's a metal, okay? And based on this, I know I mentioned this. Let me back up to my periodic table here that polonium here is indicated as semi-metal or metal. Why is it that in my, I'll go with the lecture PowerPoint slide because this is based on the text, and the class text does not categorize polonium as, does not categorize as metalloid. Some do consider, some do not. And the periodic table I'm using here is just of the internet. Be careful when you pull stuff of the internet. Some may have slight different variations. So some do consider, but for our case, polonium is a metal, radioactive metal. Now, the oxidation number, remember now we are past half or midway to group 8, where elements tend to gain electron to achieve noble gas electron configuration. We need 2 more electrons, and the negative 2 here is the ionic charge for most group 6A. All right, group 6A, non-metals. Polonium is a metal form positive 2. Allotropes, even though oxygen here is just a new term here, allotropes are molecules of the same compound having or different, it is a molecule of the same element existing in 2 different forms or more than one form. Phosphorus has an allotrope, all right? Carbon has also allotrope, diamond, carbon, okay? These are just allotrope of oxygen. Now, group 7A, halogens, mean salt forming elements. They have 7 valence electron in their outermost shell. And if you look at the fast ionization energy, which is the trend we looked earlier on, it decreases down the periodic table. It follows the general trend. Atomic radius increases because of the shells as well. The densities increase as you go down the periodic table. They are highly reactive. They have a high affinity. That means they attract electrons towards themselves, and they give away a lot of heat when an electron is added onto their valence shell to give group 8 electron configuration. Readily react with what? Metals to form metal halides. Group 7A, they react with metals to form metal halides. So here are what you need to take home from here is the general trend on their melting point as you go down the group. And lastly, group 8, of course, they are non-reactive, all right, because of their outermost shell or the fallen shell are completely filled with electrons. That means they have 8 electrons. Remember the maximum it can take, except for helium, for helium, a maximum of 2 electrons, even though we say that group 8 have 8 valence electrons, helium is the only exception. Helium is only exception. If I look at this, there was a typo here. Please take note of argon, that this is 3s2, 3p6, not p2, 3p6. If you look at the krypton as well, 4s2 and 4p6, 8 electron in the outermost shell. So noble gases have very large ionization energy. That means it is hard to remove the outermost electron. This explains the high fast ionization energy compared to group 1, which among the special groups we have looked so far, group 1 have low ionization energy, group 8 have the highest ionization energy, and the rest just fall in between, They have the electron affinities are positive, cannot form, we cannot add electron into or onto group 8. As compared to, other, let's say group A7, which are fluorine gas, this is the atomic, chlorine gas, which is the atomic, I shall have that, bromine, which is liquid at room temperature, are diatomic, this is liquid, and iodine, molecular iodine is solid at room temperature, we say that these are diatomic. But group 8, they exist as atom. For example, helium gas, krypton gas, all right, xenon gas, they exist as monoatomic gases. These are mono means one, monoatomic. You'll never see KR2 in terms of gases, but they only exist as mono atomic. Now, hydrogen has a special position on the periodic table. You will see in some in some periodic table they have hydrogen right here because hydrogen in one instant react as group 1, and that is why it is above group 1 metals, even though it is a non-metal. What does this mean? It can lose its one valence electron, but it can also share that one valence electron. That means it has the ability to react as a metal and to react as a non-metal, as a metal and as a non-metal. Also, one s metallic electron configuration. That means it can lose that to form compounds such as HCl, but when it reacts with the metal, they form what we call metal hydride. Metal hydride. For example, sodium hydride, Na. In this case, it has gained the electron from sodium. We'll see that in chapter, the transfer of electron in chapter 8, which is the basic chemical bonding. That is the other chapter I want to start today. What I want you to do is please work on the assignments. All right. So far, if you are still working on 6, you should be able to catch up by this weekend. I will make chapter 7 quiz available. We should be able to complete it by this coming Sunday so that we move on with speed so that we get done with what I intend to cover before we wrap up the course. Any question on chapter 7? Tariq, please remain, see me after class, and we will work on that. Thank you.
One question, when are you posting the quiz again?
It should be available due by Sunday, but not later than tomorrow. I'll try to post it by end of the day so that you can continue working on the chapter 7.
Any to do on Sunday, you say?
Yes.
This Sunday?
Yes.
Okay.
So let's move on to any other question? No question? All right, let's see if I can move on to 7, I mean 8. So chapter 8 is on basic chemical bonding, all right? And a bond, basically, a bond is defined as a strong electrostatic force. Before we dive into the chapter, I want us to understand what the bond is in terms of understanding what that bond is. Chemical bond is a strong electrostatic force, all right? You should be able to define this chemical bond is a strong electrostatic force of attraction between two or more atoms. It's just force of attraction. That's just a basic definition of a chemical bond, that it is defined as a strong electrostatic force of attraction between two or more atoms in an ion or in a compound. There are 3 types of bond we will look at, all right? Of importance are types of chemical bonds you should be well rounded in. One is ionic bond. We're gonna talk about ionic bond. We look at the covalent bond. These are the most important bonds relevant to this course. Down the line, all right, you also need to understand that there is another one you'll see in Chem 2, mostly metallic bond, metallic bond, 3 types of bond: ionic, covalent, and metallic. We'll look at the properties of each one of them. All right, the metallic is a special type of bond which involve sharing of C of electrons by the atoms in a compound. We look at in section 8.1, Lewis symbol of elements with respect to octet rule. Octet from the word octave, octave stands for 8. And the reason behind formation of a chemical bond, look at ionic bond in 8.2, covalent bond in 8.3. We look at the concept of bond polarity and electronegativity, which is also a trend on the periodic table. Look at on the periodic table, drawing the Lewis structure, and lastly, the bond length. We look at the bond length resonance structure in 8.6, 8.7, exception of octet rule, that some elements, when they react, they do not end up with 8 electrons. Octet rule here states that when elements react, they can either lose valence electron, they can either share their valence electron, so that they end up with 8. We call that octet rule. And the scientist who proposed that is Green Lewis. He was an American chemist, and we'll see that in 8.1. Let's see, I've given you the 3 types of chemical bonds. This is a metallic bond that atoms are held together by a sea of electrons. Ionic bond is a type of bond where it's this transfer of electron from a neutral atom to another neutral atom, and of course electrons are negatively charged. And what that happens is, in ionic bond, there is transfer of electron from a neutral atom to a neutral atom. What this means is there is transfer of electron. The arrow indicates transfer of electron, and what this means, we'll end up with sodium, which is cation, and chlorine, which is an ion negatively charged, and the force of attraction leads to what we call ionic bond, positive, negative, positive, negative. You know from classical physics that positive to attract what? Negative. This leads to crystal structure of alternating ions, positive, negative. What you see here, this is a silver spoon, and the type of bond which hold atom in this spoon is metallic. And H2O here as a covalent bond, which is the sharing of electron. The water molecule you see here, all right, we'll see later on why this molecule assume this shape. Oxygen being red, hydrogen white, the sharing of electron. Hydrogen has 1 valence electron, and oxygen has 6 valence electron. You will see this in a moment. All right, we'll see this in a moment. And if I have another hydrogen there, there is the sharing of electrons. What I want to illustrate here is the sharing of electron. We'll come back in details into this illustration, that the sharing of electrons by 2 non-metals leads to what we call the covalent bond. So basically, ionic bond is formed when there is transfer of electron from a metal to a non-metal. So when we say here ions, you need to know that ionic bond is formed between metal plus non-metal. And what this means, transfer or electrostatic force of attraction between ions, this means cation, not necessarily sodium, but any positive and negative force of attraction leads to what we call ionic. This is cation. We looked at earlier on cation, and this is anion. It's not necessarily that ionic bond is formed between monoatomic. It could also be polyatomic ion involved. They could be polyatomic ion, such as sodium sulfate, for example. Sodium sulfate, there is a polyatomic ion or sulfate as well. So ionic bond can also be formed between a metal, all right, plus a polyatomic ion. So when we say ion, ions here, it's not only restricted to monoatomic anion, it could also polyatomic cations, such as ammonium with a 2 there, sulfate. This is a polyatomic cation, and the type of bond which exists in between that is ionic bond. So given a chemical compound, you should be able to predict the type of bond which exists in that compound. This has ionic bond because there is a metal and a non-metal. There is a metal and there is polyatomic ion. If you don't know how to classify an element as a metal and a non-metal, then this can be a challenge to you. Please revisit again classifying of element as either metal or non-metal. Now, covalent bond here, the type of bond you'll see here, covalent bond, which is the second type of bond, is formed between non-metal plus non-metal. So by looking at the chemical formula, you should be able to tell that there is a covalent bond, because I know this is a non-metal, this is a non-metal. And these non-metals, they share what? Their valence electrons, valence electrons in their outermost shell, sharing of electrons. I used earlier on the sharing of electrons here to show you the covalent bond. Sometimes you may have seen this before. We will see this later on. This is the shared electron. And this is the covalent what? Covalent bond. So far, you should be able just, before even you draw the structure of the compound, looking at the element involved, in that by looking at the chemical formula, you can tell that this compound has a covalent bond. I mean, this is the type of bond we're looking at. H2O, for example, all right, CO2, for example, dinitrogen tetroxide. By just looking at the chemical formula, you can tell that there is covalent bond in that, and they are formed by sharing of electron. What these type of bonds here give rise to the properties you may have encountered, all right? These give rise to the physical as well as the chemical properties of compounds you may have dealt with or you will deal with. For example, why nail polish vaporize? Got to do with the type of bond. Why can't water evaporate at room temperature? Okay, it got to do with the type of bond. Why is tablespoon not soluble in H2O? When you start H2O using the silver spoon, why is it not that it's not dissolved? Why is it that sodium chloride dissolve in H2O? All those questions are explained in the type of bonds. You will see that. Before we look at the Lewis structure, let's see, there is one clip I want to play. I posted online. Let's look at it. Will explain in a different way. Before we come back to this, there's a clip I want to play. It's a YouTube on module 8, which explain the difference between the metallic bonding. You can just come back here again and play all this, but one thing I want to show you is how does the metallic bond compare to the ionic bond and covalent bond. Let's see, and you'll have a better understanding and insight.
Which looks better, this or this? Seems clear to me. Buy 2 pairs of glasses. Okay, this is a tutorial on metallic bonding, and we're going to be looking at the electron C model of metallic bonding and how that can explain such properties as malleability, conductivity, and luster. So the properties of metals can be understood by looking at the atomic structure of metallic bonding. But first, let's get reacquainted with the ionic bond, because if you understand the ionic bond, that's going to make it a lot easier to understand what the electron C model is telling us. So here we have a metal reacting with a nonmetal. The transfer of the electron, the reaction, results in a positive ion and a negative ion. So the ionic bond is simply the electrostatic attraction between the positive and negative charge that the ions have. So you could call this a sodium atom and this a chlorine atom. And once the sodium loses an electron, it becomes Na+, and the chlorine gains that electron and becomes Cl-. So the sodium ion and the chloride ion, being oppositely charged, are electrostatically attracted. And so that opposite charge results in a crystalline structure where we have an ongoing array of alternating positive and negative that are all attracted to each other, and that keeps the crystal together. Let's look at the arrangement of atoms in a metallic crystal. Very similar to the organization of an ionic crystal, however, they're all positively charged. And just looking at this illustration, you would think that the atoms would completely fly apart by repelling each other due to the positive charge. But if we take a closer look, the electron C model tells us how the positively charged cations in the metallic crystal can stay together. So as an example, we'll take a look at aluminum. Looking at the subatomic structure, we can see each aluminum atom has 13 protons, but only 10 electrons. It has given up the 3 valence electrons to what is called the electron C. This is why it's called the electron C model. The space in between each atom is filled by the valence electrons that have been given up by each metal atom. So the metal atoms become cations, positively charged ions, and the valence electrons are loose in the spaces between the cations. So what's holding the crystal together is the electrostatic attraction between the positively charged cations and these free-floating negatively charged electrons. And so the valence electrons are not localized to any one particle. They are free to move and occupy the space between the positive ions. And so similar to the electrostatic attraction that holds the ionic crystal together, we have this attraction of opposite charges that are holding the metallic crystal together. So aluminum giving up 3 electrons means that all the cations have a 3+ charge, and each aluminum atom has contributed 3 electrons to the sea of electrons. This creates quite a strong attraction, and we can use this model as a way to explain various properties. For example, there is malleability, the ability to put pressure on a piece of metal and not have it break. So we can pound metal with a hammer, we can pound it into a shape and not have it break. How can this model explain that phenomenon? Well, let's hit it with a hammer and see what happens. Ooh, one last blow. Okay. So as you can see, the atoms were shifting. They didn't break apart. Hitting the metal with a hammer does not break it. Why would that be the case? Well, the delocalized electrons are always there. So any shifting positive ions are going to be able to be held together by their attraction to the constant presence of those valence electrons, that sea of electrons that the atoms are attracted to. And malleability, of course, is also intimately related to ductility. You can force the metal into the shape of wires. So this is malleability. And a nice contrast would be to look and see, why does hitting an ionic crystal not result in this sort of malleability? When we hit an ionic crystal, it shatters. Let's hit this ionic crystal with a hammer and see what happens. So no matter how you hit it, you're always going to come to some point where like charges are lined up. And so if like charges are lined up, the result is going to be a great deal of repulsion, and that's going to split the crystal. And when ionic crystals cleave, they often leave a very sheer, smooth face if you do it carefully because of the way the opposite charges line up. All right, back to metallic crystals. So why would this very strong attraction result in other properties? How about their strength and high melting point? Well, the atoms want to stay together. They're very attracted to the sea of electrons. And so therefore, the higher the amount of valence electrons given to the sea of electrons, the tougher the metal, the harder it is, and the higher the melting point. Transition metals in particular, like titanium and molybdenum, each of which contribute a large amount of valence electrons to the sea, they are very tough metals, very strong, very high melting points. How about electric current? Can this model explain that? Well, electric current is simply the movement of charge. And electrons are constantly moving through these spaces between the cations. They therefore are very able to carry an electric current. And that also explains their heat conductivity, the fact that they can move through the crystal. And what about the shininess, the luster of metals? If you think about where light comes from, the emission of visible light from electrons, well, the sea of electrons, these valence electrons, can very readily absorb and re-emit visible frequency photons, and that makes metals very shiny, very lustrous.
So that is the difference between the metallic bond and compared to covalent bond and ionic bond. At least you now understand why sodium chloride will shatter if you use a hammer to hammer a crystal of sodium chloride, because you align the positive and negative. But for metallic bonding, the positive cations will just be floating around in a sea of electrons, which explain why you can pull metals into thin wires, that means ductile, or why you can make a thin sheet of metals when you can hammer, you can pound it to form thin sheet of metal because of the electron arrangement. So with that, please, there's some, I left the YouTube on covalent and ionic. You can watch during your own free time. Let's look at 8.1 Lewis symbol and the octet rule. As I said earlier on, Green Lewis, all right, he was an American chemist who proposed that when elements on the periodic table react, they make use of their what? Valence electron. When elements form chemical bonds, they make use of valence electron. From the YouTube we just watched, you had valence electrons, you know, being donated into the sea of electron, the outermost what? The outermost electron in the valence shell. Now, Lewis was the first person to propose that when elements combine, they form chemical bonds using valence electron. And we can, or elements can either lose or gain or even share their electrons so that they either end up with 8 electrons, except for what? Except when we say gain, there is exception, except hydrogen does not end up with 8, does not satisfy the octet rule. All right, elements either lose or gain their valence electron. Now, Lewis dot symbol for elements here, what is going on here is the Lewis dot symbol, all right? Lewis dot symbol for elements here. What is the Lewis dot symbol for element? This represents the chemical symbol with dot around it. Dot around it, which signifies the valence electron. You should be able to use group 1. Group 1, they will have 1 dot. Group 2, they will have 2 dots, and you do not pair them up until they are singly distributed around the chemical symbol. If you look at the chlorine, 1, 2, 3, 4, 5, all right, 6, and 7. The dots represent the valence electron, which for main group, that is the A on the periodic table, the first 2 and the last 6 on the periodic table, the dot represent the valence electron. And you can use the group number, all right? You can use the group number to determine the valence electron, except for helium, of course. You only pair them up for helium. It's the only one you can pair them up. And so, of course, not what? Not 8, not 8. So remember, the Lewis symbol for element is basically the chemical symbol, and the dot representing the valence electron. The losing and the gaining here, let me explain what is going on here, or what determines which element will lose, which element will gain. If you think about 1, 2, 3, 4, 5, 6, 7, and 8 here, group 1A, group 1, these are stable, all right? Everybody wants to be financially stable. So element as well want to be electronically stable. That means once they attain 8 electron in the outermost shell, we say that octet rule has been obeyed and the atom at that point is stable. So if an element is in group 1, it will either gain 7 more to be 8 or lose 1 to be what? To remain with 8, which means group 1 will lose, group 1 metal will lose 1 valence electron. Group 2 will lose 2 valence electron, except for beryllium. Group 3 metals, and remember we have to say metal tend to lose, not anything on the group 3 will lose. We have boron, which is a metalloid. It will not lose, but it will share its valence electron, the 3. Group 4 consists of both non-metals, both metalloids and both metals. You have to be careful when you look at that. The point I'm trying to say here is we are working towards 8. So anything closer to 8 tends to gain. For example, group 7 will gain one more electron to P8. So it will not lose 7. It will rather gain 1 electron to P8. Therefore, losing is for metals, and the number of electron loss corresponds to group number. The number of electron gain, all right, will depend on what needs to fulfill the octet rule, Let's see. Yes.
For group 4, how do you know if it's going to gain or lose? Because it's like right in the middle.
Yes, that's a good question. That will it gain or will it lose? It depends on which element you are dealing with. Once we get to a given compound, you can tell that this has gain, and especially if it is P low. Let me show you by looking at the periodic table here. How do you know whether it is going to group 4 here? I know I have lead here, which is a metal, so I know it will lose. It will not share, right?
Right.
Yes. Now, S, that is one thing I'll know, like, is it a metal? Coming back, even thin, like group 4, thin is a metal, number 50. Coming back to now an element such as carbon, you will know that, or methane, this is methane. It is made up of what? A metal, no, non-metal and a non-metal, and this consists of covalent bond, and covalent bond are formed by sharing of what? Sharing of electrons. So that's how I know, even though I may have these two, these are group 4 elements, but how will I know which one has loss, which one are? It will go back to the basic of ionic compound, transfer of electron from a metal to a non-metal. That's one criteria I will use so that I know that these will gain, these will lose the electrons. Make sense? Hello?
Yes, sir.
Yes, so I'll look at the compound in question. That will be a hint on whether it's positive or sharing for that. But for most part of the compounds we'll be dealing with here are non-metals, covalent sharing. It will be clear. Back to the Lewis symbols for elements, recall, all right, how to write the correct symbol for correct Lewis symbol. Sometimes it is called dot symbol, all right, which means dot representing the valence electron. For chlorine, you expect to have 7 dots around it, and you do not pair until they are singly distributed around. And then I look at this right here. I do have 7. This one, the last one, does not have 7 dots around it. 1, 2, 3, 4, 5. This one has 5, and this one, the last one, is wrong. This is correct. The only difference is the position of the unpaired. We call this lone pair. We have to be familiar with some of the terms when we say pair. Yeah, lone it is, that means it is unpaired, all right? We're gonna talk about lone electron unpaired. Maybe the proper term here I should have used to be clear is unpaired. That means it is standing by itself. So correct answer for this is the first two are different Lewis structures because of the different placement of unpaired electron. The last one is wrong. So the first two are correct, all right? The correct answer for this is B. Question on Lewis structure 8.1 is, I may give you and say which one of the following is the correct Lewis structure for maybe xenon, or I may give you a chemical symbol such as maybe something like that and say which group does this dot structure represent because of the valence electrons this is group A. That's what I would just be revolving around the Lewis structure for symbol. I know you did this P4. I know you did this.
For that question, why wouldn't C be the correct answer?
Are all these why C? No, because the Lewis structure, the right has only 6. On the right, this one is right? You see this?
Yeah, I was just saying, because you said that B was correct answer here,
But
but
if you look at this, Lewis structure on the right has 6 valence electrons. 1, 2, 3, 4, 5. Does it have 6?
no. So then I guess my confusion would be, since the first two are correct symbols for that, then why would B be the correct answer there?
If you look at this, why B? Let's look at, we know, of course, A. Let's use elimination and see what we do. This is, of course, wrong, right?
Right.
No, the first two are different Lewis structure because of the different placement of unpaired. Yeah, if I look at this, you understand that first of all, at the outset, we should have 7 what? 7 dots around the chlorine symbol, correct?
Right.
And the first two, they do have that, it fulfills that, right?
Right.
But the last one on the right here has how many valence electrons?
Well, that one's showing less than it should have, right?
No, but how many are there?
5.
5, right? So if I look at B, no, the first two are different. Yes, which is, the first two is correct because of the different placement of unpaired electrons, which is correct. Now, this one, C, no, because the Lewis structure on the right, this one, right?
Right.
It means has only 6, but if you say 6, I don't see 6 here.
Right. Yeah. I guess I got confused before because I almost thought none of them would be right. Just because reading it with B there, it seemed like it was almost saying that the first two wouldn't be right because they had different placements. But I was just reading it kind of weird.
Oh, okay. Yeah. Yeah, but see, the right one does not support, but the first two are, but the last one that doesn't have the correct placement of what? Placement of electrons around the chemical symbol. But C is defective in the sense that you are saying the right one has 6 valence electron, yet it doesn't have 6. So I'll go with the most appropriate being B, which is the first two are correct chemical symbol for chlorine with the correct pairing of electron, with the lone or unpaired electron being placed in the opposite. But this one is wrong. We say the first two. But this one is, we are saying it is wrong. We didn't say the right one is correct. Okay? So that's what I look at. Now, still on the Lewis structure, there are dash paired electrons. There are dash paired and dash unpaired electrons in Lewis symbol for fluorine. If you have that, that means you need to do what? The dot symbol for fluorine. Fluorine is number 9, so I need to put 9 electrons around. 7, it is in group 7A, which means we have dash paired. We have 1, 2, and 3 paired, and 1 unpaired electron. Should be 1 here, 1 unpaired electron. The correct answer is B, 3, which is still the same. So you should know the paired and unpaired electrons, paired and unpaired electrons.
Whenever you're writing the structures, does it matter where the unpaired one goes, just so that I know for future reference?
No, it doesn't really matter where you put it.
Okay.
So long as you pair them up, okay? So long as you pair where it should be, you don't pair them when you go. You start pairing when you go to 5th, 6th, 7th, and 8th. Doesn't really matter where you place. Ionic bonding, I explained this earlier on. This is something you should know. We have gone through the ionic bond, transfer of electrons. You can read that later on in organic chemistry. You'll see these arrows, which indicates the flow of electron or the movement of electron. That electron is not moving from chlorine to sodium, it's the other way around. Which you should understand that in ionic bonding, there are transfer of electron from a metal to a non-metal. And at the end of the day, both elements will have 8 electrons, which means octet rule is obeyed. What I want to point to you is the parentheses here indicates that the electrons are on, or the transferred electron is on chlorine now, or any other element in question to form the ion, I know from the YouTube, you watch the simulation on how the crystal structure is shattered when the positive and positive are aligned and negative are aligned. This explains the brittleness. When we say brittle, because of that arrangement of ions in the crystal structure. The cleavage, that means splitting, they form as smooth lines because of repulsion, Now, the amount of energy required, all right, the amount of energy required to break the ionic bond, all right, is called the lattice energy, all right? And it's measured in what? It's measured in kilojoules per mole. To break an ionic bond, all right, such as in sodium, we use, or rather instead of using a line, if there is an attraction between sodium and chlorine, this bond here, to break this, we need energy, which is called the lattice energy, which is the amount of energy required to break the crystal structure for an ionic compound. They are highly endothermic. That means it takes energy to break. That means you need energy to split. But when you form, energy is given up. They are both the same, but they have different sign. They have different sign in terms of the simple. Change in this means lattice energy required to completely separate ions in order to separate the atoms into ions which form the crystal structure. The energy required to completely separate 1 mole. Remember this per mole, that means we have Avogadro number 6.02 times 10 raised to 23 ionic units or formula units. To separate this Avogadro number, we need in terms of sodium chloride. This is only for sodium chloride. I don't want you to think that it's all the same for other ionic compound. There is a way of using the similar approach we look in SS law. We call Born-Haber cycle. Two scientists came up with the method of determining the lattice energy, which is the amount of energy required to separate 1 mole of crystal or lattice crystals for an ionic compound into respective ions. First is the ionization, the atomization from the solid, and then ionization, and then you combine to form the solid. I will not go in details on how to use the Born-Haber cycle into that, but just to look at the trend on lattice energy. For some few ionic compounds, this is a trend which you need to understand, look at how it is changing and why. Based on the prior, all right, based on the prior periodic trend in chapter 7, you should know how the atomic sizes changes as you go down the group, which explain why we see this trend on the lattice energy. If I look at the lithium, they are the same. If I draw, assuming that I'm able to have a constant, if I'm able to have a constant radius for lithium, let's say we have lithium, lithium, and assuming they are the same. But if you go down, that means this is getting bigger and bigger and bigger, the ionic radius. Recall that if you have a smaller piece of stick, it is so hard to break. You will need a lot of energy versus when you have a longer one, and when it gets longer and longer and longer, it will be much easier to break. You can use that method that if this length here is short, when it gets larger or longer and longer, it will be much easier to split. Therefore, the lattice energy keeps on decreasing. That it is very easier to break a long stick compared to the shortest one. It's gonna need a lot of energy. This explains what you see on the trend here, the trend for potassium as well, the trend on cesium. I would say based on the anion, the ionic radius of an ion that is negatively charged, it keeps on increasing down the periodic table for group 7, and therefore lattice energy keeps also increasing. Well, if I look at the group 2 here, this is magnesium, which is above strontium, all right? This is the size of cation. It increases going down the periodic table, and therefore it is much easier to ionize, all right, the lattice energy for strontium because of that same analogy here. In this case, cation is getting larger and larger going down the group. You see this magnesium, calcium, strontium, and so forth. That is the general trend you need to look at. There is also the effect of the charge, that the greater the charge, all right, the greater the lattice energy. In other words, the ionic charge play a role also in terms of the amount of energy required to break that. It increase with increase in charge. All right, so we look at that. This is group 1 metals, and if you look at the increase, I think we looked at this as is decreasing as the ionic radius of cation increase down the group. Likewise for anion, if you look at the same, it increase in cation radius, anion radius, and it follows the trend. Question here is, place the following in order of decreasing magnitude. That means from the most to the least decreasing ionic radius. So if I look at this, for that question, sodium is up here, followed by what? Potassium is right here, and rubidium is below, Rp is below, so that, and this one, and this one, it is getting big and big. So if I want to see fluorine, sodium fluoride, it is small, so I'm gonna have just something like that compared to chlorine. All right, chlorine is a little bit bigger than that. How about bromine? Is sodium bromide, so it is bigger than Br, like that. So if you look at the size, just using the size of cation, size of anion, all right, the question is placed decreasing from the most, so that means rubidium will have this will be the easiest. So we want a decreasing. That means this will be number 3, this is number 2, and this is number 1. So the correct answer is D, which means Rp, rubidium bromide, decreasing. No, yeah, decreasing. That means sodium is the other way around. This will be the first one. I wanted to, depending on the increase, this will be 1. All right, this will be 1 in terms of increasing the highest. So this will be 1, 2, and 3. This from Mars, you know what that means, right? Greater than. Potassium chloride, greater than rubidium, what? Bromide, Br, like that. You know, this means greater. And of course, this one means less than. This means less than. So if we are to increase that, the correct answer is from the most energetic with the high energy, sodium fluoride, to rubidium fluoride, sodium fluoride to rubidium fluoride.
Sorry. Whenever you're looking at the periodic table, so am I correct to assume, at least as a general rule, that as you go down a group, you're going to decrease your lattice energy, and then as you go across across periods, you're going to increase your lattice energy?
Yes, 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 yes.
Okay.
It is because yeah, as you go down, because it's getting larger and it's easier to break. All right. So that is what affect these general trends. Next time, maybe according to increase in lattice energy, or which one will of the following will have the most lattice energy or the least lattice energy, according to increase in lattice energy, according to decrease in lattice energy, something like that. But it will call for understanding the general trend on lattice energy on the periodic table. Now, having come through the 3 types of or 3 methods of writing electron configuration, you should be well-rounded in all the 3. All right. We are using that as the foundation to write the electron configuration of ions, and ions are either positively charged or negatively charged, which means for negatively charged means you have added extra electron. And the overall charge on the ion indicates how many electrons you have extra. The overall positive charge indicates how many less electrons you have. So if I were you, I will write the general electron configuration for a neutral atom and then do the math that how many electrons should I remove, and then you end up with the correct number of electrons. For example, let's see, sodium, you know, this sodium, this has 1s2, 2s2, 2p6, and then 3s1. This is neutral, but when we have sodium positive, we are less by 1 electron. So it is 1s2, 2s2, 2p what? 2p6, and then the 3s1 is gone. That is basically writing the electron configuration for sodium ion. We are less by 1 electron. Magnesium will follow the same, all right? This is 1s2, 2s2, 2p6, and then 3s2, 12 electron. But overall charge of plus 2 means we are less by 2 electron, 1s2, 2p, no, this is what? This is 2s2, 2p6, all right? We are less by 2 electron. And remember what we said earlier on, Mg positive and N positive, we say isoelectronic. That means they have the same electron configuration. Just to give you a recap on what isoelectronic have the same electron configuration. For non-metals, they tend to gain electron. So if I have chlorine, this is 17, 1s2, 2s2, 2p6, 3s2, this is 12, and 3p5. Remember, overall charge of -1 means we have extra 1 electron, and what you'll end up with this is 1s2, 2s2, 2p6, 3s2, and then here 3p6. We have added extra electron. We have added extra electron for chloride ion, I think for the S and P block elements, it's very easy to write electron configuration for ions. I want you to, you know, look at how to transition metals right here, the D block elements. Earlier on, we had to fill in the 4s before the 4d. Let me write electron configuration for iron, for example. Iron, which is number 26. This is 1s2, 2s2, 2p6, this is 10, 3s2, this is 12, 3p6, this is what? This is 18. We go to 4s2 and then 3d6 for number 26. This is neutral atom. If I were, or if someone asked you to write the electron configuration for iron 2, all right, iron 2, somebody will think that you remove the 2 electrons from the 3D. No, you start losing electron or removing electron from the highest N value. And the highest N value here is 4s2. Therefore, this will be 1s, what, 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d6. The 4s2 is gone. Uh, 4s2 is gone. All right. Sometimes you may see this. Argon has 18 electrons, and then I'm just gonna write 3d6. That is what I'll end up with for iron 2 ion. Likewise, for iron 3, you will end up with this. 1s2, 2s2, 2p6, 3s2, that's 12, 3p6. Now, the 4s2 is gone. You start with 4s2 and then 3d5. So I remove the first 2 from the 4s sublevel, and then the 1 extra electron from the d sublevel, which means we are less pi 3 electron. That's the pattern you follow in dealing with transition metals. We do not follow the octet rule. Transition metal loses valence electron fast. Valence electron, and remember valence is that which is then lose the d electron. So you remove the 4s and then you go to the d sublevel. So this can be argon is number 18, followed by the 3d5, followed by the 3d5. Please remember how to write the electron configuration for elements, especially what I've underlined in green. Somebody may think that you fill in the 3D and then you go to 4S. No, you don't put the 3D here and then the 4S there. No, you don't do that. It's not going to work. You may Google out elsewhere, they might be doing that, but as far as we are concerned, follow that table I gave you earlier on orbital filling diagram, the zigzag that cross the diagonal arrow, join the tail and the arrow, and then you will have the right order in which the sublevels are occupied, the electrons according to increase in energy. For SNP, as I say, for SNP block element, it's very easy to write the electron configuration for ions. For the transition metals, remember to remove the 4s first before you start removing the d electrons, depending on the charge, of course. If it is 1, it is 2. Question on the screen, question on the PowerPoint slide is, based on the octet rule, magnesium most likely forms a dash ion. This will call for understanding, the periodic table that it is in what? It is in group 2, it will form magnesium 2. Common mistake I see in the exam is somebody will just pick this. They don't know. They don't know the chemical symbol for magnesium and they say that is correct. It turns out that in this one, you have the correct chemical symbol for magnesium. The question is it positive 2 or negative 2? Metals tend to lose their, of course, valence electron, as I said, and the correct answer is A, magnesium ion. This is manganese. This is manganese. Make sure you know the periodic table, the group number and how to predict the ionic charge, Phosphorus, based on the octet rule, phosphorus is most likely to form which ion? Phosphorus in group 5, and 5, all right, 5 means 3 extra electron, and phosphorus, which we call phosphide. By the way, this is called phosphide. We call phosphide. And it is a phosphorus ion. The correct answer is B. It will gain 3 electrons, 3 electrons. We will start from 8.3, read on covalent bonding. Next time, read on drawing the Lewis structure. 8.4. Chapter 8 is pretty straightforward. If you mastered chapter 7, periodic trends, recall the periodic table, recall the groups or special names for those, and the valence electron, it will be much easier for us to write the Lewis structure for molecules, chapter 8, 8.4, which is critical for chapter 9. We need to be able to write or draw the Lewis structure for molecules or ions. I will start from here on next Tuesday. We'll see how far we'll go on Tuesday. As I said at the beginning of the lecture, please be on the lookout. I will post quiz 7 due Sunday. More information will be shared. I will post today's lecture and Tuesday lecture. You missed last Tuesday, should be available shortly. Tariq, please stay, stay behind, and I will address your question or your concern. Other than that, the class is dismissed. I will see you again on Tuesday. Thank you and have a wonderful day. I'll now stop sharing my screen.